Okay, so hello everyone. Welcome to our 5th virtual SI session. This is going to be the last one.
Sad life.
So the topics we're going to be covered are going to be listed right here. Let's go ahead and get started. So the first topic is knowing the difference between exothermic and endothermic. Exo and endothermic is basically talking about the change in enthalpy, which is delta H. For anything that's exothermic, it means that delta H is negative. So an example of this is when you form bonds. And this is because energy is being released, because the atoms that have an attraction for one another are being brought back together. For endothermic, that's when the change in enthalpy, which is delta H, is positive. And an example of this is when you break bonds. If you think about it, breaking bonds requires energy to be absorbed or added because you need to put in energy to break something, like a twig, for example. So here's just like some extra examples. One example is like when you burn wood, that is exothermic. And an example of something that's endothermic is when you're melting ice cubes because energy has to be put in to melt the ice. So let's try some practice problems. Determine whether each scenario is endothermic or exothermic. So the first one is cooling water down from 89 degrees Celsius to 22 degrees Celsius. And we can use phase changes and temperature changes to help determine if a process is exothermic or endothermic. So the three phases of matter are solid, liquid, and gas. So to help us determine what is exothermic or endothermic or not, we need to ask ourselves which phase has the lowest energy. So which phase has the lowest energy?
The lowest energy. Oh, that was me. Okay. So the one that has the lowest energy would be the phase that has the least amount of movement. So out of the three phases, solids would be the ones that have like the least amount of movement. So that's the reason why it has the lowest amount of energy.
Yes, that is correct. So solids have the lowest energy because they're really stable. Their molecules don't move around as much. They kind of just like vibrate, and they're really packed together in a nice, stable structure and formation. Liquids have the next highest energy because their molecules are more flowing, they're more loose. And gases have the highest energy because their molecules are just flying around everywhere. So now that we know which phase is like lowest or highest in energy, we need to think about changing phases to determine if something is exothermic or endothermic. So let's try, for an example, in order to move to a higher phase of matter, like from a solid to a gas, do you need to add or remove energy?
You would probably have to move solid to gas. So if we're going from solid to gas, that would be endothermic. So that means we had to add an energy.
Yeah, so because solids have a lower energy state and gases have a much higher energy state, in order to excite those molecules, you need to add energy into the system. So this process will be a endothermic reaction or endothermic process because you're adding in energy to make it move to a higher phase of matter. And then in order to move to a lower phase of matter, like for example, liquid to solid, do we need to add or remove energy?
Well, let's see. So if we're going to go from, we know that solids have the lowest energy. If we're going to go from liquid to solid, that means energy has to be released from the liquid to be, so that the particles can get closer to the solid form. So it would have to remove energy.
Yeah, so that is correct. Because liquids have a higher energy state than solids do, if you want to make something go from a liquid to a solid, you need to remove that extra energy so that when it goes to the solid phase, it'll be much more stable and there will be less movement of the molecules. So that's why moving from a lower phase of matter will be exothermic. because you need to release that excess energy. Alrighty, so based on what we just went over, cooling water down from 89 degrees Celsius to 22 degrees Celsius will be an exothermic reaction because you're moving from a higher state of energy. We know that at high temperatures, molecules are more excited, so they move around a lot more than at lower temperatures. So in order to get from a higher temperature to a lower temperature, you need to remove some of that excess excitement or that excess energy. So number 2 is boiling liquid water at 100 degrees Celsius. And this will be an endothermic reaction because when we boil liquid water, we're trying to go from a liquid state of matter to a gaseous state of matter. So we're trying to move from a lower energy state to a higher energy state. And in order to do that, we need to put in some type of energy, whether it be from like putting it on the stove or putting it over the fire, or adding energy into our system. So that makes this process endothermic. And then number 3 is burning wood. So this is an exothermic reaction because the wood is being set on fire. It's releasing a lot of excess energy. If you think about wood, you can think about it like being from a solid state, and then when you set it on fire, you see smoke coming out of it, and you see an increase in the surroundings temperature. So all that exothermic energy is being released in the form of heat energy. So that's how we know this is going to be exothermic. And then lastly, we have water vapor condensing. When something condenses, it's going from a gaseous state into a liquid state. So again, this is a change from higher state of matter to lower state of matter. So we need to remove the excess energy from the excited gas molecules so that they can be more stable and less energy in the liquid state. So this would be an exothermic reaction. Okay, next we have calculating heat of reaction. So the symbol we use is delta H naught of reaction. The delta just is the symbol for change, so change in heat. And then the little circle, that little knot thing that we call, is at standard conditions. So I think this is 25 degrees and 1 mole. I'm not too sure. I can like double check that really quickly. So this can be done in 2 ways. The first way is to use Hess's law. And in Hess's law, we need to use multiple chemical reactions and then add up each of their heat of reactions. A second way is to use the heat of formation for individual compounds in a single chemical reaction. And the formula we use is going to be products minus reactants.
Times the respective moles, right?
Yes, but we will get to that later. So let's try Hess's law first. A good way you know that this will be a Hess's law problem is if they give you multiple reactions. You can't use Hess's law necessarily if you're only given one chemical reaction, because it requires the knowledge of previous reactions to help you add up everything and solve for a delta H reaction. So let's find the reaction, the heat of reaction for this chemical equation if we're given these 2 extra ones. So here are the steps. First, I recommend flipping the reactions so that the products and reactants are on the correct side. And when you do this, you need to remember to flip the signs on the heat of reactions too for those equations. So the reaction we want has CH4 on the reactant side. But in the first equation we're given, CH4 is on the wrong side. It's on the right side. So we're going to have to flip this first equation. And that's what I did below. I flipped it so that CH4 is on the left side, which matches the CH4 on the equation we want. And then everything else is going to be on the opposite side. And when I did that, I also flipped the delta H of reaction. So originally it was negative 75 kilojoules, but when you flip the products and reactants, you need to change the signs too. So it's going to turn into positive 75 kilojoules. Okay, so CH4 is on the correct side. Now we need C2H6 and hydrogen gas on the right side. So in this equation, it looks like C2H6 is on the left side. So we want it to match the same side of this equation. So we're also going to have to flip the bottom equation as well. So when you flip it, you should get something like this. And then you should also get the heat of reaction to be the opposite sign. So it used to be negative 85, but when we flip it, it's going to turn into positive 85. Okay, so now that our reactants and products are on the correct sides, we need to multiply to cancel out species and in order to match the coefficients of the reaction that we're given. So because there's a 2 in front of CH4, but there's no 2 here in the equation that we were given, we're going to have to multiply everything by 2 in order to match that coefficient. And then when we multiply all the species in the chemical reaction, we need to do the same thing for the delta H of reaction. Because the delta H of the reaction, it's only for the equation that we're given. So if you multiply everything by 2, we need to also do the same. So when you do that, you should get this equation right here. 2CH4 turns into 2C plus 4H2. And the delta heat of reaction is going to be 150 kilojoules. And then we don't need to modify anything for the bottom one because later, when we do step 3, we're going to add up both of these reactions and heat of formations to simplify the reaction. And when you do that, you'll see that the 4 hydrogens or 4 hydrogen gases on the top right side, will cancel out the 3 hydrogen gases on the left side. So when those cancel out, you're left with only 1 hydrogen on the right side. And that matches what the original equation wanted. And then the 2 carbons will cancel out because they're both on the opposite side. And then all you have left over on the left side is going to be the 2CH4. And you always want to double check if your equation matches the equation that they're giving you, just to make sure that you didn't cancel out anything accidentally or you messed up on your math. And then finally, we're going to do the same thing for the heat of reactions. So before, when we multiplied everything by 2, we also did that to the heat of reaction. So when you add these 2 reactions up, you're also adding their delta heat of reactions. So it's going to be 150 plus 85 kilojoules, and that'll give you positive 235 kilojoules. And then a bonus, because they might ask you this on an exam, is this reaction an endothermic reaction or exothermic reaction?
Well, we know if it's positive, it should be heat gaining, so energy gaining, so it should be endothermic reaction.
Yes, so that's correct. If you did the math and your delta heat of reaction, for example, came out to be like negative something, then the answer to that would be exothermic, because when delta H is negative, energy is being released, and that makes it an exothermic process. But for this one, this would be an endothermic because delta H is positive. Okay, so we're good with Hess's law. Another way to calculate heat of reaction using heat of formation. So a good way to know the difference between which one to use is based on how many equations they give you. So here, you're only given 1 equation, but you're also given heat of formations. So heat of formation is basically how much energy does it take, or heat energy does it take to form 1 mole of this certain compounds at a certain temperature, which I think is 25 degrees Celsius. or standard temperatures.
Around there.
So we're given this reaction, and we're given their heat of formations in kilojoules per mole. The first step is to set up an equation, which is going to be products minus reactants. And we do this by determining the sum of the heat of formations. Sorry, I need water. Of the heat of formations for the product and the reactant. So when you do this, you also need to remember to add up or to multiply by the coefficients. Basically, if you look at the product side, which is right here, we have 1 mole of CS2 and 4 moles of H2 gas. So when we set up our equation, we can write it like this. There's going to be 4 moles of H2 gas times 0, because that was the heat of formation, plus 1 mole of CS2 times 89 kilojoules per mole, which is the energy it took to produce 1 mole of that product. And then you're going to subtract from the reactant side. So 1 mole of CH4 times negative 75 kilojoules per mole plus 2 moles of H2S times negative 21, which is the amount of energy it took to create 1 mole of that. But since we have 2, we need to multiply it by 2. And then when you do the math, you should get 89 minus negative 117. Oh, and then your answer should be positive 206 kilojoules. It's really important that you use plenty of parentheses and brackets when you're typing these calculations into your calculator, because a lot of times students will get confused with their signs and whatever. So definitely don't skip steps for these problems. You don't want to mess up on a problem just because you couldn't do the algebra, for example.
I can explain why it's 0.
Yeah, go for it.
Yeah, so I'll explain on the other side. So the reason why that H is 0 is because it's a pure substance. So anytime when you have a pure substance or something that's found in nature naturally, we'll have a heat of formation of 0, which revolves around. So did not work. Thermodynamics. So up to this point, you're familiar with Hess's law and heat of formation. So those are concepts of thermodynamics. So there are about 4 laws of thermodynamics, but for now we only had to focus on these 3. So the 0th law of thermodynamics: any 2 systems that are in thermal equilibrium with each other and with the third system, then if 2 systems are in thermal equilibrium with a third system, then they are thermal equilibrium with each other. So that means if the energy of A is equal to the energy of B, and the energy of B is equal to energy of C, then energy of A must equal to that of energy of C. So it's kind of like, how do I say this? If you think about it, it's like, what's a good example for that? Like A is equal to B, B is equal to C, then A is equal to C. There's not like a math property for that?
I don't know.
Okay, but we'll just say that. So the first law of thermodynamics. So energy can neither be created nor destroyed. Same thing with matter and mass. So conservation of energy, conservation of mass, they intertwine with each other. So the reason why that the reason why the H2 gas is 0 is because it does not require any energy to form it. Heat of formation is the one that calculates how to form delta H, calculate the heat of formation. A pure molecule by itself, or anything that's found in nature naturally, is considered 0 for heat of formation, but not entropy. which is the second law. So the second law is the total entropy, which means disorder of a system, can never decrease over time. So the nature of molecules, they always like to make a mess. So you can see this room right here, it's in a mess. So molecules don't like to sit around. Think of them like little kids. You know how little kids, they don't like to sit around for like an X period of time. They want to always move around back and forth, like they're just like filled up with all that sugar energy. Same thing with entropy. They always like to have everything in disorder. They don't want just to sit around. They want to keep moving. So the more disorder, the more entropy. The lower disorder, the less entropy. So, and then specific heat is basically the amount of energy that is required to heat up a substance over 1 gram of substance over temperature. So, okay. So, heat transfers mostly goes from a high energy state to a low energy state. And you can never, so a good final question is that, can heat transfer from low to high? Is it possible? Is it possible for energy to transfer from low to high?
No.
It is. Unless through work. Through work, it can transfer from low to high. But naturally, heat can never transfer from low to high. It's impossible. If we could do that, then we would never have an energy crisis, if you think about it. So unless through work, heat can transfer over from low to high, but never naturally itself. It always high to low. So energy is always conserved. So the system has to lose energy. So surrounding. It's supposed to say surrounding. How do I edit this? It's supposed to say surrounding. Yeah, that looks way better than my handwriting. So it's the surrounding. So the system has to lose energy, and the surrounding is the one that gains it, and vice versa. And that's also a form of endothermic and exothermic reactions. In order to find heat, we mainly use Q is equal to MC delta T. Q is the heat, M is the substance, and C is the heat capacity, and delta T is just the change of temperature between one energy state to another. So then, why don't we move on to the next one? So here's a problem. So you're given an iron ore that weighs about 200 grams, and you dump this ore into 3 liters of water. Shit, did I not change that? I changed it to 1 liter later on. My apologies. It's supposed to say 1 liter too. Double check your math, kids. That's important. Let's say 1 liter. Sorry. 1 liter. All right, to 1 liter of water. The temperature of the ore was around 504 Kelvin, and the water was initially 15 degrees C. They both reached the equilibrium temperature. So what is that temperature? Assume the following constants are true for this problem. So heat capacity of iron, which is this, heat capacity of water is this, and density of water is that. So, important question. How will we solve this? What's the key word that sticks out in this problem?
Equilibrium.
Equilibrium, right? So if it's an equilibrium, that means the temperature of that means the temperature of both of these, the water and that of the iron ore, will meet in the middle. Can we solve this problem without knowing it's in equilibrium?
No.
No, it's impossible. There's no way for us to meet them both in the middle unless we know that they're in equilibrium. So why can't we? So I already answered the why. All right, so moving on. But yeah, let's see here. Next slide. Oh, they both reach the equilibrium temperature. That means we know that the temperatures, their final temperatures, will equal to each other. So then, we use the formula Q is equal to MC delta T. Now then, how many equations, so how many unknowns do we technically speaking have? What temperature do we not know?
The final temperature.
The final temperature, right? The final temperature of what specifically?
Water and iron.
The water and the iron. So that's 2 unknown temperatures. You know what that means, right? We don't need 1 Q is equal to MCP delta T. We'll need 2 of them. So we know that the heat of the water is equal to the mass of the water times the heat capacity times the final temperature in the water. And we know that the iron energy is equal to the same thing, but in terms of the iron. And of course, we have T final and T final here. Now then, going back, what do we know about energy? What's important? Huh?
Has to be conserved.
Has to be conserved, right? Energy must be conserved. That means that if one will be gaining energy, the other one will be. If one's gaining, then what's the happen to the other one?
Losing.
Losing, right? So that means. So which one of these two would you think would be the one that's losing and the other one would be gaining?
The ore is losing.
The ore is losing. Why is the ore losing?
Because it's hotter than the water. So when it touches the water, it's going to give some of its energy into the water.
All right, there we go. And what kind of process would that be called?
Exothermic.
Exothermic, yes. It would be exothermic. And then the water would be doing what?
The water heating up is endothermic, but the ore cooling down is exothermic.
All right, so that means the direction of heat, which is the sign for the Q iron, should be
negative, and then water is going to be positive because it's gaining energy.
Yep. So Q iron, so the negative heat of Q iron will equal to that of the positive Q water. So the heat that's being released from the iron will go into the water. Now we can solve this problem. Shit, did I change it to 1? I did change it to 1. Whoops. Okay, so the mass of the iron times the C in the iron times the final temperature, times the change in temperature of that of the final minus the iron is equal to the mass of water times the heat capacity of the water times the final minus water initial temperatures. So then, this is the formula. I just set them both equal to each other. I included the negative symbol there because we know that heat is going from the solid iron ore to the water. And that also agrees with thermodynamics. Heat always likes to transfer from high to low. So the higher energy state will go down to the lower energy state. So then, Shaniqua, change that to 1,000. Change this to 1,000. I had a panic attack when I was making the formula. So this is supposed to be 1,000.
No, it was just me. This wasn't done. So just to make sure sushi was all right and make sure that if they did go to the back.
1,000 grams. So then, 200 grams comes from the iron ore. 0.45 is the heat capacity times the final temperature minus the 504 Kelvin. And then 1,000 grams, because it's 1,000, times 4.184 joules per gram times TF minus 288. Now then, here's an important thing. Heat capacity may have units of degrees C or Kelvin. I know that a lot of students in class always ask, do I need to convert? It's up to you. It's whatever makes you feel comfortable with, if you want to change it to Kelvin or not. But the thing is, the change in temperature, the change in temperature does not matter. That one always stays constant. What changes is if you change so example, let's say you have 20 degrees C minus 10 degrees C. You know that equal to 10 degrees C, right? But if you had 273 of that, that's a whole different. That's not the change in temperature. You just converted you just converted degree C to Kelvin. So always make sure that the heat capacity, make sure that your change in temperature is always consistent with your heat capacity. What I like to do personally is I like to convert it out to match the heat capacity for change temperatures. Yes, it's a little bit more work, but at least, I know my units will cancel out. So then, moving on. Next. Oh, wow. Maybe I should not change the problem. Oh, who cares? All right, so here are the values. Here are the values of it after I do all the math for it. This is also supposed to say 200. Always check your math, kids. And then finally, you should get a final temperature of around. Okay, so I distributed all of the values out. So -90 times, so it's the mass times the heat capacity. That's where -90 comes from. 450, 60, 80 is the one where I calculated the heat capacity times the temperature times that of the mass. So it's just distributing up all the numbers. And then here's more of a clarification of it. I want the TF to be on one side and then all the energies on the other side. And then I divide them all out and I end up getting it in a final temperature of around 292 Kelvin. So, yeah. But for 1 liter. This is for 1 liter. All right, so then, intermolecular forces. Viscosity. Viscosity is just the friction or the resistance of a substance. So if you think about it, you spill water all over your table. It's easy to take it out, right? It's like so simple to take it out. If you spill maple syrup all over your table, then that's where you get the what are you doing? Because maple syrup has a higher viscosity than that of water. So it's more like viscosity likes it for it to stick onto material. Water, of course, doesn't really want to stick on material as much, but since syrup has a higher viscosity, they'll more likely be the one to stick on material. So the higher you go, so the more the stronger the viscosity increases over depending on what kind of material you're using. Surface tension. So, Claire, have you ever belly flopped before?
No.
Oh, well, I did. And it hurt like heck. So that used to be me back then when I used to be, not a swimmer. But moving on. So surface tension is the elasticity. So what surface tension is the elasticity tendency of a fluid's surface, which makes it acquire the smallest surface area. What does that mean? Well, according to Wikipedia, that's what it says. Definition: the more surface area you have, then the higher the higher elasticity you will have. So, example, let's think about this. Have you ever tried, jumping on well, let's take the belly flop for example. If you were to do a cannonball, right, and you go into the pool of water, will it hurt a lot? Will you feel a lot of surface temperature?
Wait, what? Surface temperature?
Yeah, so example, surface tension, sorry. I'm thinking in my lab. Surface tension. I meant tension. Sorry. If you're a cannonball and you jump into a giant pool of water, will you feel any tension with the water, without the water?
No.
No? Why?
Because you're a ball.
Because I'm a ball, right? The smaller the object, the less surface tension it has, meaning it has less surface area. if I lay my body out like a belly flop and try to smack myself into the water, the surface area increases. That means increases the surface tension. All right, so your boy is really, damn it. Okay, so adhesion, cohesion. So adhesion, the tendency of dissimilar particles or surfaces to cling onto each other, and cohesion is just the opposite. So think of it as like, I don't know, what's a good example with adhesion, cohesion, like a real life example? You got one, Claire?
Water. So for cohesion, it means that water molecules tend to stick to one another. So, but then for adhesion, it's a tendency for water to stick onto other surfaces. So for example, if you see like water drops on like a window after draining, adhesion is the water droplets clinging to the window. But then cohesion would be like the water droplets clinging to each other to form that little tiny droplet.
Right. So that's correct. So yeah, I like it. That's actually way better than I would have thought of thinking of an example. But yeah, so cohesion is always just like molecules like being attracted to each other, and adhesion is just two different molecules. So add, dissimilar, co-attract. You gotta, there's a strat for that, but it's fine. All right, and then the other molecular force that you recently went over is capillary action. So the ability for a liquid to flow through narrow spaces without assistance. So have you ever done gardening before? Like, you know, when you're like a 10-year-old kid and they give you a little seed and they say, here, go plant this, kid. So how it works is that, or let's see here, all my biologists out there, you've seen, or physiologists, or anyone that studied the human body, you know that there's three main bloodstreams in your body, right? The arteries, the veins, and what's the last one? The arteries, the veins, and what's the last one? Your capillaries. So your capillaries are the ones that, well, how do I say this? They're the ones that filter out your blood between both that of the arteries and the veins. So how capillary action works is that they're very, very narrow tubes that allows that you don't have to force them through from point A to point B. It just naturally goes through it. So same thing with plants. The roots themselves, they are actually the capillaries of the plants. So, you know, when you water the plant all over it, that's the reason why you don't water the plant on top of where all the leaves are, is because they're not gaining any water. The only way they're going to get the water is through the roots, which are buried in the soil. So once you water your plants, the roots will be the ones that will have is the capillaries, and that's where the water will go up into the plant and throughout the system. Same thing with that with your blood. Same thing with that with your blood. The blood moves through your capillaries, very narrow tubes, without the need of assistance from any other outside source. So then, next up, partial pressures. So partial pressures. We got our boy Dalton over here. Look at that. We're like twins, right, Claire? Claire, we're like twins, right? So Dalton's partial pressure. So with how to find, so the total pressure is equal to the sum of various pressures. You've seen that in lab. I think it was experiment 11 or something. 11. So Dalton's pressure. So the total pressure in the mixture of gases is the sum of partial pressures of each of the gases. So when you have when your system is filled with various gases, each of those gases had an initial pressure, and that pressure itself is called the partial pressure. Now then, why don't we take a look at that? So here's a problem. The mixture of oxygen, hydrogen, and nitrogen gases exerts a total pressure of 208 kPa. if the partial pressures of oxygen and hydrogen are 112 kPa and 83 kPa respectively, what would be the partial pressure exerted by the nitrogen? So you have the total pressure, you have the pressure of the hydrogen, and you have the pressure of oxygen. You're looking for the pressure of nitrogen. Well, simple as that. All you have to do is take the take the pressure of oxygen and pressure of hydrogen to the other side, and just solve for PN2, and that's how you get that one. So that's more of a simple version of partial pressures. But we'll try something more complicated. So there are 3 tanks with various gases in them. Container A has a volume of 2.0 liters and a pressure of 800 torr. Container B has a volume of 2 liters with a pressure of 700 millimeters of mercury, and container C has a volume of 4 liters and a pressure of 1 atmosphere. If all 3 volumes are added into the same container, what is the total pressure? Well, let's assume in this case, let's assume that temperature and number of moles for all of them are constant. So if we know that the number of moles and the temperature is constant throughout, whose law can we use? Whose law? Whose the law allows us to do this, Strat?
I don't memorize the names.
All right, well, that's what I do with them. So we're going to do with you too, Claire. Ready for this? Oh, no, wait, go back. Draw. Oh, turn on. Here we go. Draw. Here we go. Ready for this, Claire? Oh, whoops. Oh, shit. All right, turn on. I can do this, coach. Claire, ready? Whose law?
Oh my god.
You can do this. Whose law is it? Give me a letter.
Dalton's?
It's not Dalton's.
Just tell me, like, I don't know. I don't memorize the names.
Fine. Well, first off, let's imagine our containers. Time is over. All right, fine. Well, let's just imagine our containers then. All right, so let's imagine we have 3 containers. Container A, container B, container C. We know that each are the parameters of all of them. So we're going to mix all of these three containers into one giant large container. So the important question here is, what is the volume of the large container? If we're adding all 3 of them together, assuming that moles are constant, temperature is constant, what's the volume of this container? It's 8. So, in order to solve the partial pressures, we use Dalton's law of partial pressures to find the total pressure of the container. We use Boyle's law of pressure and volume to find the partial pressures of each of the gases in the container. Do note that the total pressure is the same of that as the external pressure. So then, why don't we go into solving this a little bit? So how to solve it? Well, according to Boyle's law, we know that P1V1 is equal to P2V2. P1 is the pressure of the gas initially, V1 is the gas initially. P2 is the pressure of the gas in the final container, and V2 is the volume of the container itself. So to solve for P gas of A, in the final container, it's P2A. So the pressure to find the pressure of A in the final container, it's B2A is equal to P1A times V1A divided by V2. P1A being the pressure initially of the gas A, V1 is the initial volume, and V2 is the total volume of the container. And the same two apply for T2 and P2C. And then to find the total pressure, it's just the sum of all of them. And with that, you should get around, let me see my problem again. You should get around about, let's see. You note that your pressures must be in the same unit. So make your life easier and just put them all into ATM. Because you know the conversions of ATM between all of them. It is technically speaking the same thing if you think about it. 700. This one, 760 divided by times 2, or parentheses, 777, too many parentheses, 777 divided by 760, close parentheses, times the 2, close parentheses, divided by 8, close parentheses. Okay. Plus parentheses, parentheses. 4 times 1 divided by 8, close parentheses, about 1.2. Oh, shit. Exit screen. That's awkward. About 1.2. Oh, it's my workspace. This is awkward. So 800 torr divided by 760 torr is equal to 1.0526 ATM, and then 777 millimeters of mercury divided by 760 millimeters of mercury is equal to, that is so awkward. My handwriting's so atrocious. I hate everything-ish. Just kidding. I love everything. 760, 1.0223 ATM, and the other one's 1 ATM. So these are the conversions of just putting them all into ATM. And then after that, you just multiply each of these by the volumes. So 2 liters in the first one over 8 liters, which is the final one. This one is 2 liters divided by 8 liters. Come on, you. And this one's 4 liters divided by 8 liters. And when you add all of these up, the total pressure should equal to around 1.02 AT. So that's the total pressure in your container. All right. So why don't we just clear everything? And finally, what is diffusion? What is diffusion? So diffusion is the rate at which the gas particles are able to escape through a small hole. So the smaller the hole, then the lower the diffusion rate is. But again, it depends on the gas particle. The larger the hole, the faster diffusion. What is diffusion? The rate at which gas particles are escaped through open pores. So if you have a balloon, depending on what gas is filling up the balloon, will depict if you will have a faster diffusion or lower diffusion. So helium will diffuse, so like helium gas versus like nitrogen gas. We know that nitrogen is a larger molecule than that of helium. Since helium is such a small molecule, it can slip through more of the pores than that of the nitrogen. That's the reason why that one. So let's imagine the blue balloon is helium and the green one is nitrogen. So helium is a lighter gas, so we can see it like float up a little bit, while nitrogen is more of a heavier gas. So that's why it's like more down into the ground, seen in the picture right here on the right. And then we see that since helium is so small, we already know that it doesn't take that much of space than that of nitrogen. So we know that helium will diffuse faster because it's a smaller molecule. So that's how fusion and diffusion works. So finally is the last slide. So how to study for the final. Well, first things first, rely 100% on virtual SI sessions. We can't guarantee that we covered everything that will be on the final, and we could have missed some stuff too. Google is your best friend, and so is YouTube.
Yeah, just be careful of your sources. That's the only bad thing. And then from Dr. Kelly, so at our meetings, we have like these weekly meetings with her, and we asked her, what should students do to study for the final? And she recommends looking at her lecture overviews on Canvas. So she literally looks back at those overviews as she's writing the final to determine like how many questions and like what types of questions of each topic will be on the final. And then she also wants you guys to look at your modular quiz results, because they will show you which topics you might need extra help in. And then another thing that she mentioned was that when she was an undergrad taking Chem1A and all that stuff, she would write like study guides about or on each exam and each quiz that she took, so that by the time it was time for the final, she had like a bunch of these little study guides and like overviews to look over or to look at, so that she was better prepared and had a better like sense of like how to pace herself to study for the final.
And also probably just like, whatchamacallit, know what your struggles are, know what you don't get, know what you do not get. I would say my personal experience with studying, polish up what you know already, and then work on something that you might not know or probably kind of feel that you're not really good at, and then you work on something harder, so you increase your difficulty. To me, I like to work in the middle, so like if I don't know what I'm doing initially, then I go back to step one, see how it is with like how I did the basics with it, and then try to apply it with the new change, and then see if I can do something harder. So it depends on like how your study habits are, all what it is. If you like to study in groups, make sure you make some good friends or probably some lab mates. That's what I did too. I studied with a bunch of my lab mates when I took Chem1A. And also, if you know the material very well, why not teach it? Teach it to others that not really know how to understand it. I think it was, did you take Sing Master's summer week thing, Claire?
Yes.
Yeah. And and Sing Master said that one of the best ways for you to learn is if you're able to teach it to another person.
Yes.
Something like that, yeah. So if you know the material very well, try if you can explain and teach it to someone else. That's another efficient way of how people can learn, because our terminology might be a bit, not the same as that to all of yours, because as you advance, you start to forget some of those words. That's the reason why it takes us like a while to even think about some of the words itself. And we don't really polish it of ourselves because we don't really look back into it. But as your Chem1A right now, look back all of the work that you've done, and then see okay, I understand this. Maybe if I can explain it to my roommate or my sister or my brother or my mom and dad, they might fall asleep after the first 2 minutes of me explaining it. But it's just how you explain it will help you understand. And yeah, I think that's it. Do you have any?
I don't think I have.
Oh, so sorry. Might be. So reminders, please remember to sign in to the Google Sheet for your attendance with your name and ID so we can keep a track of attendance. And thank you for tuning on. And we'll see you all on lecture on Monday for the last time. Bye, everyone.